want to start, thank you him for accepting the invitation. I know you have a very busy schedule these days because I have been part of them. And you cannot believe it, to give you a picture, after lunch, he has to get back to Madrid, an interview with the media, then an interview with the sponsors for the Climate Finance Conference, tomorrow the governor of the central bank. So thank you, Rob, for coming. And let me introduce him. All of you know maybe his CV. If you make the experiment of going into GPT chat and you type CV Rob Engle, you get a good summary. So I'm not going to do that. So I'm going to tell you things that I'm sure GPT chat do not have yet. So I'm going to give you a personal impression that I hope Alvaro, where is Alvaro? Alvaro, you also are going to share these personal thoughts. Rob Engle and Clive Ranger, they are the Nobel Prize in Economics recipients in 2003. And totally unrelated, they were the PhD advisors of Álvaro Escribano and me. These two things are not related. No, it could be a causal relation because they were first, but there is not anything. Yeah, that it could be, but no causality. We predicted. In fact, talking about prediction, my value as a forecaster is almost zero. I thought we were going to be only 10 people here. So because of the exams and people are very busy. So I also have to thank all of you for making an effort to come. So let me tell all of you that Rob is one of the colleagues I most admire. And the admiration comes because I tend to admire people I learn things from. And I know that you didn't notice, but I have learned many things from him. So let me only summarize 3 things. And later on, Rob, Alvaro, if you want to say something also to add. No, to add. I learned 3 things from, at least 3 things. First, if you want to master in a topic, you have to write a paper on that. It's the best way. You can study lecture notes, a book. No, write a paper. So I remember Rob was not a very, let's say, close friend of asymptotic theory. Rob wrote a paper, Handbook of Econometrics, with the 3 most important tests in '84 or something like that. Rob wanted to be master in Kalman filter and EM algorithm. He wrote 2 papers with Mark Watson, very influential 2 papers. He said, okay, let's talk about the stream events. Caviar, with Simone Manganelli. Why not non-parametric, with my close friend Gloria Gonzalez? Let's go a little bit further than factor analysis. Common feature, co-features, with Sharon and Farshid. So this is the first advice for young people. You want to learn something, write a paper on that. And Rob is very, very good on that. The con, so this is the pros, the con that sometimes becomes difficult to publish because you are not a world expert in that topic, because you are learning that topic. But this is something that I try to learn, and I try to do it, but not very successful. The second thing is an advice that he gave me, and I'm sure he doesn't remember. The summers where I was in Boston, as a faculty member, I used to fly back to San Diego because the weather in Boston is even more horrible than now this here, and in San Diego is, well, the perfect weather. And once chatting in his office, I don't know the excuse, he said, Jesus, econometrics has to be used. We have a huge value added. Find a topic and use the econometrics. He have already found the topic, was finance. In my case, at that time I haven't found any topic. I was thinking of maybe consumption, investment, and later on I found the topic of climate, and I tried to imitate a little bit. Hey. So I think the time gave him the reason, because now there are any serious study has a deep, deep quantitative analysis in that. So econometricians, young econometricians, don't get depressed. We have a huge value added. And seriously, I mean, sometimes value added that we don't even know. I'm sure you have checked that. You go into finance and you are able to define things and test things that people in finance may say, what? What is that? So the last thing that I learned many things, but I'm going to, I mean, he's the speaker, not me. So the last thing is this job, the academia job, is a long-term and job or hobby, as some people in my village, they say, well, but you like to work in your job, no? I say, yeah, fine, no. Okay, that is a hobby, and you have to be in very good shape. And Rob is, let me tell you something that maybe you don't know, he's almost a professional ice skater. He has won several medals at the US level in his age range, adult competition, and collaborated, correct me if I am wrong, with some even Olympic medalist, Russian female there. So Rob, I mean, goes high, high, high. No, I'm not going to run a test if you have to guess his age, but believe me, he's in a very, very good shape. So the three advices are, if you want to learn something, write a paper, find a topic where you can, for econometricians, where you can have value added, and be in good shape. So otherwise, you're going to have a very bad time, no? And the last but not least, if you have a Nobel recipient in your family, I guess you may think that he's the most famous in his family, no? No? Makes sense, no? It used to be, but now not anymore. The most famous in his family is his mother-in-law. So don't hate mother-in-law. So his most famous, the mother-in-law, is a psychologist, is an Auschwitz concentration camp survivor. He had interviews with Oprah Winfrey that you didn't. So he's on teaching education, on the TV, this. So if you want to have a look at, go into internet and check for the book, The Choice is one of them. It's a very, I mean, I recommended that. So without no more introduction, thank you, Rob, for coming and accepted, well, to be like a normal seminar. And we remember the times in San Diego, so this will be like San Diego with a lunch in the coffee room. So nothing fancy, but this is a, okay, thank you, Rob.
I mean, I don't think I have anything to add to that. Actually, I thought that what I would do today is basically new research, which I have given once, which was last week. And I thought we're going to just have a nice little conversation about it. But I see a lot of you came, so we'll have a big conversation about it. And it's so nice to be here. I mean, I have visited Carlos Teixeira several times in the past. I have so many wonderful students that have been teaching here and studied here maybe before that. And it feels like a very special place to me. So I'm glad to be here, and I really appreciate all of you coming on late notice and hot weather and so forth and doing this. So I want to talk about something called compound tail risk today. And we sort of know about tail risk and compound. It sounds like it's going to be multiple things at the same time, and that is, in fact, what we're going to talk about. So if we think about risk management, when we've got risks in the future, things that could happen that are bad in the future, what do we need to know about them? We want to know how bad is this risk if it happens, and how likely is it to happen. And with that information, an investor or an owner or whatever can make the decision as to whether the reward is worth taking this risk. So we sort of have to know these two things about it in order to really make this decision in a rational way. And that's what risk management is about. It's not really about avoiding risks. It's about measuring them so that you can decide whether or not it's worth taking them or not. So that sounds very good when we're talking about one risk at a time. You can decide whether to take this risk or not. But when there are multiple risks, and there is a view that we're in a time when the number of risks that we're facing is growing and the complexity of our world is growing. How do we do this? Well, I'm going to try to set up a framework for doing this, and I'm going to think about it as, two risks, because two is a bigger number than one, and it's only just a step away from lots of risks, I guess. But anyway, we can think about it that way. And so one of the ways that we analyze these risks is with a stress test. So what you do is you say, okay, the risk is that this stress might actually occur, and you want to know what the probability is and how bad it'll be if it occurs. So when we have two risks, there's a question of whether they'll both occur, or one will occur, or the other one will occur. And that's sort of the issue we're going to be trying to talk about today. So let's take a case where we know kind of how to do this, but see how we would deal with it as a stress test. And that is, you've got a portfolio and you've got stocks in it and you've got bonds in it. So we can think about this not just as the risk on the portfolio, but the risk on stocks and then the risk on bonds. So if we try to define a stress test, we might think that the stress on the stocks might be that they're going to drop 40% over the next 6 months, whereas a similar stress on bonds might just be a 10% drop in bonds. So where does this come from? Well, roughly these numbers happen about 1% of the time in terms of 6-month returns. So these are both events that you would say are extreme but plausible. And stress tests love those words, extreme but plausible. And of course, we're going to try to be a little more quantitative about what we mean by extreme and plausible. So if we look at the risks in our portfolio, we would say the risk from a stock collapse is that the portfolio is going to go down 24% if we have a 60-40 portfolio. And 60-40, I mean, it's widely recommended sort of division of your portfolio, but it says you're 60% in stocks and 40% in bonds. Okay, so that would give you a 24% decline in the portfolio from the stock event. If the bond event occurs, it's only 4% decline. So this is the way risk management often looks at these problems. They look at each risk one at a time. But the question that we're going to try to ask today is, okay, now what do you do with these two numbers? Minus 24 and minus 4. Do you add them together? Do you look at the max? Do you notice that the stock is much riskier than the bond and say, okay, we want to do one or the other? And I think that this is the solution that risk managers face with compound risk is exactly that. Not how do you do them one at a time, but how do you combine the answers you get from these different stress tests and try to understand what really is the risk of your portfolio. So compound risk is common. It's what risk managers and regulators deal with all the time. We had a conference, as I mentioned, a week ago, 2 weeks ago, I guess, by now. And one of the speakers said, and we commissioned actually 3 papers for this conference as well as some others, discussions and so forth. And one of the commission papers said, you know, think about January 2019. If someone were to come in and tell you that we need to worry about a pandemic that's going to kill 500,000 people, we need to worry about a drought that's going to decimate half the US, wildfires that are going to rage in the Sierras, going to be a flood in Houston, there's going to be inflation like we haven't seen in 50 years, and the first ground war in Europe in 50 years, more than that, I guess, what would you do? I mean, this is super compound risk of a lot of bad things. And his answer was, well, you'd throw the guy out of the room because you just could not imagine that all these things could happen. But of course, they did happen. And one of the things I wonder is, suppose you knew for sure they were all going to happen, what would you do? Well, that's not an easy answer to give either, is it? You might take all your money and move to Bermuda or someplace, but probably you'd be worse off for doing that than living through it. So it's complicated. Anyway, so the point is that risk managers are faced with this kind of problem. And what do they do about it? Or what do we think they should do about it? Here are some more examples. We're going to talk in some detail about climate risk and market risk happening at the same time. But then there's physical risk and transition risk within climate risk. There's market risk and liquidity risk in financial markets. Market risk and the risk that I like, which is the risk that the risk will rise. Inflation risk and unemployment rate, we're talking about that all the time. Climate risk and pandemic. Macro risk and credit risk and interest rate risk, those are often put together. And then we have everything, everywhere, all at once, which, as you may know, won the Academy Award this year and is kind of a makes the statement, I think, in a way. Okay, so clearly, combining these risks into a compound risk requires knowing something about the joint probability of the realizations, and that's obviously where we have to go today. In particular, the probability that one risk has an extreme realization when another risk has an extreme realization is something we'd like to know, and that's going to be kind of a key parameter. What are the chances that two different things, each of which is unlikely and extreme, they both occur? And so let's talk about some properties of this joint distribution that we're interested in. Let's look at the extreme quantiles of two distributions. Let's call it the distribution of x and y. So there's a probability that x is going to be less than qx, and a probability that y is less than qy, and we can pick qx and qy so they give the same probability, which we'll call u. And that's going to be some tail probability, something like 1% or 2% or 5% or something like that. So then the question is, what's the probability that y is less than its quantile given that x is? And if you write down the rule for conditional probability, you realize it's the joint divided by the conditioning one, but the conditioning one is the same as here, so these two are the same expression, and so there is no, it's a symmetric relationship when you define conditional tail events like this. And let's call this lambda as a function of u, the probability that we're talking about. So we're interested in this for small values of u because we're thinking of both of these as being events that, if they're bad, they're big negatives. They're down. So like stock market or something like that. So u is a small number, and we can take the limit as u goes to 0 and get something which we call tail dependence. And tail dependence is a parameter that we might be able to estimate for two random variables like this. So the first thing to do is to say, okay, suppose we knew what the tail dependence was. How does that solve the problem? What is the problem? The problem is to choose qx and qy, and probably we're going to do that by choosing u. But it might not be the u that we already have. So one of the things about these tail measures is that it's fairly clear that you don't need to know the whole distribution in order to find the quantiles of the tail. And so, we only need order statistics to know how far out in the tail we are. So in a sense, the distribution theory from this is possibly simpler because we don't need to know the whole density function, we only need to know the density of the ranks. And when we talk about joint densities, we have a word for the density function of the ranks, which is it's a copula. And so the tail dependence is a function only of the copula, not of the whole density function. And as you can probably see from the way I've set this up, you know, if you ranked all the data and then you looked at the 1% quantile, you just know which observation that is. And you can ask whether other things are more extreme than that or not, basically just knowing all the ranks of the data. So what are the values of lambda that we actually know already? So one thing is that x and y could be disjoint, so that you can't ever have both of them, in which case this conditional probability is going to be 0, right? Another case is that x and y are independent, and this might be the natural starting point for these stress tests. You could think about, are these stresses independent? And if they're independent, that means the conditional probability is equal to the marginal. And the marginal has a probability of just u, so that lambda of u is going to be u, right? Okay, I don't want to lose anybody at this stage, because it's easy, but it might be unfamiliar, I'm not sure. Or maybe it's familiar, or maybe, I don't know. But anyway, so in any case, if lambda of u is equal to u, then the limit as u goes to 0 is obviously 0. So these two cases turn out to be the same. Independence and disjoint are equally good from the tail point of view. But the case that we're sort of particularly interested in is if x and y are perfectly dependent. So that means every time x is in the tail, y is in the tail. In that case, the conditional probability that x is in the tail given that y is in the tail is just 1. And so lambda of u doesn't depend on u, it's just 1, and it's so the limit is 1. All right, so we can think about lambda bars going from 0 to 1 as being the case of where they're essentially independent or disjoint all the way to the complete dependence. And then a lot of interesting cases might be somewhere in between. And one of the reasons why we think we might be able to solve this problem more easily than actually building the whole joint distribution is that you don't have to know nearly as much to estimate the tails of a distribution as you do to estimate the whole thing.
One
Yeah.
comment. So if lambda is 0.3 versus lambda is 0.7, do I have a feeling whether I am in a very bad situation or even no? It's not.
Okay, let's do the next slide. So what are we going to use this lambda bar for? So, oh, maybe it's 2 slides. Okay, so I have here's my formulation of the question. I want to pick qx and qy. And I want to pick them so that the probability that x is not extreme and at the same time y is not extreme is 1 minus alpha. Why do I want to do that? Well, if x is not extreme and y is not extreme, then I don't have either of these tail events. And so the losses that I'm going to expect are not as bad as qx and qy. And consequently, I can say, with probability 1 minus alpha, I have a lower bound for what losses could happen. And that's what I want. And I'm going to call that the stress loss. And if the value of your firm is a nice linear factor model like this, it says that the rate of change of the value of the firm is beta x times x plus beta y times y plus an error term which has mean 0 conditionally on the x and the y, then the biggest loss we can expect is beta x times qx and beta y times qy. And I'm going to call that the stressed loss. And it's like sort of like a value at risk measure, but it's different, but it's similar. Okay, so if I can find qx and qy that satisfy this relationship, then I know that the loss of this, the expected loss given x and y, will be greater than, or not, in other words, not as bad as the stress loss. So I'm going to be looking for stress loss here, and I'm going to try to pick u so that this relationship is satisfied. And so since I'm going to pick qx and qy, I'm assuming I don't know what betas are yet. That qx and qy are the stress portfolio. This is what, say, the central bank is trying to construct and tell all the banks they have to use the same scenario. And then the banks have different beta x and beta y's, which tells you how much loss they might have. But even a risk manager might not know what his beta x and beta y are. He wants to choose the qx and qy, and then he might hold those and watch what happens to the value of the firm over time as the betas change and stuff like that. The betas are the 60-40 we used in the first example. That tells you how much exposure you have to x, how much exposure you have to y. Okay. So how do we do this? Well, the solution is to pick a u star, which is going to define the quantiles for y and x. So they're not, even though we're going to start thinking we want a 1% quantile, we're going to have to look up a u star quantile. And what's u star have to look like? This is the equation that has to satisfy. Alpha is going to be equal to 2u star minus the probability that both of these happen at the same time, which is approximately lambda bar times u. Why is that? Well, because the probability of this joint event is u times the conditional probability, and the limit of that is u times lambda bar. The approximation is u times lambda bar. So if I want an alpha portfolio, I've got to choose u star so that alpha is equal to 2 minus lambda bar times u star. So if lambda bar is, well, I think this is next slide actually. So if lambda bar is equal to 0, which means that these are tail independent events, then it's just alpha over 2. And if lambda bar is 1, which means they're all both the same event, then 2 minus 1 is just alpha. So u star is going to be alpha. So you don't have to change your quantile at all. You just add the two numbers together. But you only add the numbers together because it's really the same event. If they're really different events, then, you know, the probability, the sum of the events is greater, obviously, than each of them separately, but the probability of the two events is lower. So to control the probability, you have to change the tails that you look at. Okay. What about if you have 3 risks? Well, if you have 3 risks, the probability that all three of them occur at the same time is maybe very unlikely. If you're willing to make that assumption, then you can derive this formula in exactly the same way. So it's alpha over 3 minus the lambda between 1 and 2, 1 and 3, and 2 and 3. And one way to do this is with a Venn diagram. And if I had a magic marker, I'd just put it up here on the wall, and we draw these circles, and you say, okay, what's the probability of being outside of all these circles? Well, it's probability of not being in this one, not being in the second one, not being in the third one, but then you've got to add back all the little intersections between them. And that's what's going on here. And you can presumably generalize this to higher dimensions should you want to do that. Okay, so back to the stock and bond example. So if these two events are tail independent, then we're just going to choose U star as half of alpha. And there's one of the reasons people like the stock bond allocation is because a lot of times when the stock market goes down a lot, people put their money in the bond market because that's a safe haven. So the bonds go up when the stock market goes down. And you actually see often negative correlations between the two. However, last year, if any of you were actually managing money, you noticed that both stocks and bonds went down at the same time. So it can happen. It might be that inflation is different from a recession. So, you know, it might be that's another risk we need to add in here, and then we would get the whole thing right. But in any case, if we assume that these things are tail independent, then what we're going to do is we're going to use a 0.5% quantile rather than a 1% quantile for both stocks and bonds. Going to use alpha over 2. And so, I don't know, you look at this up. Okay, so now the 0.5% quantile for bonds is 11%. The 0.5% quantile for stocks is 48%. You may wonder where I got these exactly, but the answer is I used every day 6-month returns on an ETF for stocks and an ETF for bonds over the last 20 years. So like 5,000 observations, but they're super dependent because they're overlapping. And you can just take the quantiles of this. And that's what I did. Now, you might think about whether that's what you want to do, but that's what I did. Okay, so anyway, the stress loss here is 33%. And that you have a 99% probability of not losing that much on over the next 6 months. Okay. Actually, I should point out here that all the returns I'm going to talk about are continuously compounded, which means I'm going to show you a couple cases where it's bigger than 100%, which you initially say, wait a minute, that can't be right. But in fact, 100% in log returns translates to like 60% in fractional returns. So it's not a paradox. Okay, how did this actual portfolio do over the last 20 years? Well, it turns out there was one 6-month period when it fell by 33%. During the financial crisis, but the actual 1% quantile was only 22%, and so in fact it was true that it didn't fall with 99% probability. It didn't ever fall by 33%. Okay. Well, that's one example. Here's a slightly different example, but it's different in an important way. And this is, we could think about holding US stocks and international stocks. That's another way people divide up their portfolio. And if we look at the daily quantile, we find these are pretty similar, -3.5% and -4. If we use daily data, then tail dependence seems very close to 1. In other words, almost all the events that are extreme for US stocks are extreme for global stocks on a day-by-day basis. So we're just going to add these two together. And if you have something like an 80-20 portfolio, it comes out to be, this weighted average of 3.5 and 4. And it's very close to the actual tail event. If you use semi-annual data, then it's not quite so obvious that every event where the US goes down a lot that the rest of the world does, because there are periods when the US is appreciating relative to the rest of the world and cases where the rest of the world is going down. I mean, these are long-term flows in exchange rates are part of this difference, as well as the way the economies work. So in any case, here I'm going to estimate this as 0.7. And we get a stress loss of 47%. The actual 1% quantile of this portfolio is 44%, satisfying the inequality that we expected. Okay, so this is all sort of motivation. And I think I've taken too long. Let's go. So how do we estimate this tail dependence parameter? Tail dependence is key to this thing, and there are a variety of ways proposed in the literature. And there's a nice survey here by Fram, Juncker, and Schmidt, 2005. They basically talk about, first of all, we could estimate the joint distribution and then just look at what the tail dependence is. We could also, but of course and this is the most accurate, if you know the distribution. But if you don't know the distribution, then it's subject to a lot of errors. Similarly, if we know what the copula is, we could estimate that up to some parameters and then just calculate tail dependence. That's less restrictive because the same copula applies to lots of different joint density functions. But we still are not sure what the copula is going to be. I mean, and really the issue is, are you going to use observations which are not extreme to tell you what the dependence is in the extremes? And obviously that's perilous because extreme events may really be kind of different from the rest of them. Okay, so another thing to do is to take a threshold and only look at observations that are more extreme than some threshold, maybe 10% of the sample or something like that. You have more data then, and you use a parametric tail copula to do that, and you can estimate that tail copula taking account of the fact that it's got a threshold, and then calculate what it is. But what I'm going to do is a purely non-parametric approach, which might be called the empirical copula approach, and it just calculates for different values of u how often one's in the tail when the other one's in the tail. And so anyway, this is a very simple and logical thing. So this is what u is defined as, and we know we can look for a data set. What observations have y in its tail, and for how many of those is x in the tail? Okay, that's simple to do. And the answer is, if this is plotting in terms of 10 basis points each one, so this is, I guess 1%, 2%, 3, up to 10%, we can calculates the probability that stocks are in the tail given that bonds are in the tail. And you see it's noisy, and when you get out here, you've got hardly any observations, so it's not surprising it's really noisy. On the other hand, it does seem to have sort of a slope, so that if you took the limit, you think you're probably somewhere down here. And furthermore, you see even the highest of this is just lambda's 0.1. So this is all below 0.1. So that was essentially why I said, let's pick lambda bar equals 0 for stocks and bonds. For US and foreign, the same picture looks this way. So you see that the tail dependence is rising as you go to more and more extreme events, but it isn't up at 1 at all. Okay. So this is the non-parametric approach, and it is a little bit heuristic about how do you extrapolate this thing to 0 when you have less and less data as you get close and the standard errors are big. Well, you could do a Monte Carlo and see how it works. And a simple one says, okay, y and x have Gaussian errors and plus a student t common shock. And the student t common shock has some degrees of freedom in it. If it's only got 3 degrees of freedom in it, it looks like this. And if it's got 10 degrees of freedom, it looks like this. Theoretically, we know that if it's normal, if it has infinite degrees of freedom, no matter how correlated two random variables are that are Gaussian, the tail dependence is 0. So in a normal world, we actually don't need to measure tail dependence. It's automatically 0. But you can see when student t has higher degrees of freedom, this curve is really coming down, although it doesn't look to me like it's going to hit 0. Okay, so this is kind of what you might expect for a simple model, and it looks not totally different from what we looked at from either of the first two examples. This is, of course, done more observations. This is 100,000 observations. The other two are done with 5,000 non-independent, that is, overlapping observations. Okay, so now I want to look at market risk and climate risk. And this is actually a real problem because when we start doing stress tests of the banks, we ask how much exposure do they have to climate risk? That is, are they holding a lot of oil and gas loans that are going to go down in value so that the bank is really going to lose a lot of money if those companies go bankrupt? That's a risk. But if at the same time that those companies are going bankrupt, the macroeconomy goes down so that the market risk goes down as well, then that's a double whammy for the banks. And when we do a stress test there, we want to know, should we be doing both of these things at the same time? So there are a lot of explanations for why the market would be an event that would have a relationship to climate event, partly because the market is a measure of how fast the economy is going, and that's how much emissions we're making. So the stronger the economy, in a way, the worse the environment gets. And so there is a kind of a negative relationship there. But also, if you're putting on some strong regulation or tax on the fossil energy sector, you're likely to knock the economy for a loop too, especially if you're not careful about what you do with the revenue from this tax. So you might expect them to both go down together. In any case, there's no consensus in the literature as to how dependent these would be, but we could potentially look at data to see whether there's any evidence there. So central bankers are looking around the world at how to do these kinds of climate stress tests. And I'm going to talk at the Bank of Spain tomorrow about how we do that. And I'm going to show you some of the things we're doing here. But the question immediately comes up, how do I deal with these compound risks when I do this? Okay. So in the paper that I'm going to talk about tomorrow, which is with Hae-Yoon Jung and Dick Berner, we've now implemented these climate stress tests in VLab so that you can actually see them and follow them over time. And the essential point is that we regress the stock market price of a bank on some risk factors. The common one is the market return. You get a market beta on it, but we also regress it on a climate fund. And we ask, so that gives us a climate beta. And this climate factor is a climate risk portfolio. It's got in it stocks that are at risk from climate change. And these are typically large emitter stocks, energy stocks, and so forth. And it might be short other stocks that are not so, would not be so impacted by a climate mitigation and decarbonization program. So I'm only going to talk briefly about the risk factor we use. We use the stranded asset portfolio, which basically is 70% weight on a coal ETF and 30% weight on a broad energy ETF, and then short the S&P. So this is a stranded asset risk portfolio. And if you were around Camillus University yesterday, I was talking about hedge portfolios, and you can easily go from a risk portfolio to a hedge portfolio by multiplying by -1. So in other words, if you're long a risk portfolio, you're taking the climate risk. If you're short the risk portfolio, you're hedging it. That's not shocking. Okay. So what we do is we calculate these betas, and then we calculate them using what we call dynamic conditional beta, which is a method takes account of the fact that volatilities and correlations are changing over time, and at each moment in time, we have a forecast of every volatility and every correlation. So we have estimated covariance matrices of the data and cross products between the dependent variable and the independent variables. So it's like a least squares regression, one observation, and then you update everything, and then you do it the next observation. The formula is still x prime x inverse x prime y. It's just that what those matrices are, it changes every day. So we get a beta every day, and for climate risk, at the end of the period, Citibank had a beta of 66, and a climate beta of 66, and a market beta of 1.5. So the damages from these two risks, if you treat them individually, would be, well, if we, let's see. So the 1% quantile for 6-month returns of the market is 33%, and for the stranded asset portfolio is 64%. So here are the two numbers we're starting with. So this is kind of looks the same as where we started in the stock bond example, but we have to figure out whether 1% quantile is really the right thing to use here. So if I do my little non-parametric estimate of lambda, I get a picture that doesn't look like any of the ones I've had so far. And I don't know whether to extrapolate this part of the curve or this part of the curve. And you see it goes all the way from 0 to 1. So it actually makes a lot of difference which way I think about doing this. And so, unfortunately, I don't have an answer to this key question as to whether I should treat these things as fully dependent or tail independent. So, I mean, one thing is there's more work to be done, but I'm going to do calculations anyway, and I'm going to pick a number. What's the number I'm going to pick? Well, if I pick lambda bar is equal to 0, then I have to use alpha over 2, and I would get these quantiles for the two factors. And my stress losses would be 106% continuously compounded, which is actually just 66% loss fractionally. So this says that Citibank's stock would go down by, I'd be 99% sure it wouldn't go down by as much as 66%. Well,
question. To calculate this dependence, it might depend on whether the impact of humanity is larger or smaller. Don't you think I don't know if it's possible to calculate the same risk, but call it natural risk, the real natural risk, and then separate the humanity impact on this? Because what is difficult to control is the humanity impact on the claim. The rest more, I mean, I don't know if it will be possible to have that component because it will affect the probability to fail.
so, I mean, I think both of these are human components because the mitigation is really a question of what we're going to do about it. In other words, are we going to pass laws? Are we going to tax emissions? Are we going to restrict emission allowances if we've already got a cap and trade system going? So there's a lot of human interaction in the stranded asset portfolio also, and clearly the market portfolio has a lot of humans. So I don't know how to do that separation. But I mean, I should make the point that I'm trying to ask this question statistically, but most often people would ask it theoretically. You know, what are the theoretical causes of this and that, and how do they work out, and do you really think these things are either independent or completely dependent, or how dependent are they? And I think that's where you're going. You're trying to think about what really are the drivers of this kind of behavior. And obviously we could say, well, we need to write down a whole model, which kind of is true, but if we knew how to do that, maybe we'd do it, but we don't know how to do it either. Okay. If we look at Citibank's betas, you'll see that the market beta in blue is more or less hovers around 1, which is not surprising. That's true for most stocks, or many stocks anyway. The climate beta has gone up and down over time, and it was highest in 2020 during the pandemic, and now at the end of the sample period seems to have come down quite a bit. There are various explanations for why it's come down. One is that there is a threat that regulators are actually going to pay attention to this, in which case Citi might not make as many loans to the oil and gas companies. Or maybe they're going to download some of these loans into a subsidiary or something. There might be other explanations. And so when we look actually in a little more detail, we get, let's see what, so this is now the picture of stress losses over time for Citibank. And what you see, so this is the compound risk. And what I've done is I've used the 0.5% quantile for both market and climate stress. So I've increased those stresses a little bit to get to a 1% alpha. And this is the answer. So this is combined. And when you go to VLab, if you look hard, you'll find there's a place where you can actually dial in what you want the stress to be for the market risk and what you want the stress to be for the climate risk. And then it calculates all these statistics for you. And this is what it looks like. This is what the betas look like for the market betas for the largest US banks, and this is what the climate betas look like for the largest US banks. And you can see this rise during the pandemic. It's very clear. The pandemic really looks a lot like decarbonization that we do in a rather draconian fashion, where people can't drive anymore and they can't go to school and they have to Zoom everything. So the rest of it is not really clearly up or down. There's some periods when it looks down, some periods when it looks up, but it's kind of hovering around zero. If you look at the stressed loss then, which now is for all these banks, you see for all of them it looks kind of the same. And what are we talking about? We're talking about, well, up here we're getting up to this 100% loss that we saw at the max for Citi, but mostly it comes down here and we're talking about maybe 40% loss, which is kind of like the market risk. It's not much climate risk. The betas are changing over time, but it's interesting to see that the betas for all the stocks are pretty correlated with each other. So the things that are happening in one bank seem to be happening in another bank. That's also true of the climate betas. So there are reasons to think that there's systematic stuff going on here, and maybe all the banks hold portfolios that are changing over time, or maybe the market's awareness of the climate risk is changing over time. Both of those things could change all the banks at the same time. And so there is, this is a measurement which we can make and we do, and I think it's reasonable to look at it, but there's more we could understand about how it's all happening and what the pieces are. So I guess that's what I said. Well, what about Spanish banks? Well, you can do this for Spanish banks too. And here is an application of these same quantiles to market risk and climate risk for Santander. And what you see is that here's 40%, here's an 80% loss. So this would say that you're 99% sure that the loss is going to be less than 80% if the next 6 months have both this climate risk and market risk going on. That's not all that comforting, I guess, but that's at least what the numbers say. And here is the what we call C and S risk. C for climate, S for systemic or market risk, and the dollars here that Santander would need to get itself back to an 8% capital ratio would be about $80 billion, which, while it's a big number, is not really big in these kinds of international finance calculations. And so when we talked about systemic risk, which is the S risk part of this, we said what was important was whether a lot of banks had risk at the same time, so they can't help each other out, and there's no place where you can really manage your money. So it makes a lot of difference whether this kind of magnitude is true for the banking sector as a whole. And so here's what you see if you look at the C&S risk in Spain. This is the number here for Santander, which is 82 billion today. That's the most recent. BBVA is like 25. Then Caixa, Banco Sabadell, Unicaja, so forth, down the list here. But if you look at these numbers, these last ones are all negative, which means that the bank actually is overcapitalized for even in spite of this kind of a risk. So, I mean, I don't think these numbers are telling us this is a systemic risk at this point. And so this is my last slide, and I think I'm well over time. Sorry about that. But there are so many things that this analysis is begging for, which are, first of all, we could use better univariate quantiles if we used some of the extreme value distributions to smooth them out. Second of all, better tail dependence measures using copulas and possibly threshold copulas, I think, are a topic that is very manageable and something that I've been talking with Dante about, actually. Measures of impact and whether the betas are actually nonlinear. It could be. I mean, we've got a nice factor model here, but we're talking about pushing it to the limit when we talk about, 50% decrease in returns. And is there predictability in the betas based on other information? And, well, this is a very straightforward example compared to real-world examples, which are dealing with inflation and unemployment and international relations and mortgages and all sorts of stuff. It's pretty hard to actually do all this with those, but I think this sets a framework for how to think about what happens when you're looking at these compound risks. You don't just necessarily add them together, and maybe they're independent. So anyway, okay, so this is it. Thank you.
So we have time for questions. Yeah. Okay, cool.
I don't know, it's a basic question, but I don't know, because you found a high correlation between the betas. What is the correlation with the risk factor? Because you are using the market factor and the climate factor. What is the correlation between these two factors, and is there any relationship between the correlation between these two factors and the high correlation you found with the betas? I don't know if, do you know what I mean?
Yeah, okay, yes. So
thank you.
the correlation between the market and the climate risk factor is relatively low. Because the climate risk shorts the S&P. So the energy stocks are highly correlated with the S&P, but the relative price between energy and the S&P is not that correlated with the S&P itself. I mean, it's got a small negative correlation. But the correlations between those do not carry over to tail correlations. And that's one of the things that's the reasons for doing this, is that the tail correlations are important and relatively different, necessarily a different thing from what the sample correlations are. The correlations among the betas I think of as being dynamics of the way the banks are working and doing, what their portfolios look like. And well, if technology loans become riskier and all the banks are holding tech loans, then that makes the betas change for all the banks, but it doesn't change my stress scenarios. And so that's why we can compare over time how a bank looks, because the betas are changing, but the stress is not.
Thanks. I don't know if I understand wrong, but you are using a portfolio of high emission companies as the indicator for the climate risk, right?
Right.
So that means that if it's a portfolio, huge movement of the price could be due to the market events, not just climate events. So my understanding is that that is why you have observed a high correlation between the two risk factors during the pandemic, because huge drops in the climate risk indicator that you have found is due to the market event, not just climate event. So
Yes, but the portfolio is a portfolio of energy stocks, but it's short the S&P also. So it's the relative return of energy to the rest of the market.
so it's just like a carbon premium or risk premium.
It's like that.
Oh, okay. Thanks.
More questions? Yeah, Yanis. And also the undergrad, if you want to ask questions about personal things, also feel free, not only risky.
What's happening in the crisis periods, as you're commenting, is when you go short and long in order to do the hedging, the hedge, the both go the same direction. Basically, the correlation changes is not such a strong hedge, and the add up in the portfolio risk. So you go short and long, but then in the crisis you have most bad things being positively correlated rather than negative correlated.
Right. So yes, I mean correlations are changing all the time, and that's one of the things that we've built in here. We've allowed the correlations of these risk factors to change over time. But when I'm looking at the tail correlations, I'm hoping that they're not changing over time, that they're actually something that I can measure one time and use it. But one of the explanations for why this picture doesn't look right is that they're changing over time too, and that I'm not sure quite. I don't know that any of the solutions that I put up there are going to solve that problem. So maybe we need some more ideas.
Hi, I have a question in terms of, you use a method that is backward-looking using historical data on the market, because the market is forward-looking. But I was wondering, how robust do you think this methodology is going to be in a situation that we're seeing where we have a substantial climate effects changing the structure of the economy, as also technological changes are also changing the structure of the economy. So I think we'll be living in a time where actually a lot of changes are taking place at the whole structural basis, and I don't know how stable these approaches are going to be to use them into forward-looking.
Well, I completely agree with that. Really the climate awareness is changing and the climate science is changing, and the economic analysis of the climate science is changing. So what I think we get out of this is an idea what the questions are that we need to ask. We need to ask how dependent the tails of these distributions are going to be in the future. And if we think that a climate stress is always going to produce a macro stress, which I think there's a plausibility to that assertion, then that tells us what we use for our lambda. So does that get informed by what we saw in the past? Probably. But is it purely a function of the past? No, I think you have to supplement it by looking forward. And so what we're looking for, as usual for a stress test, is something which is extreme but plausible. And I would say that when people talk about compound risk, they don't really know how to control the size of this test. And that's what we're trying to adjust here.
Okay, I am an undergrad, so I don't know if this question is going to be relevant. But as you said before, in the last 2 years, we have lived too many events in the economy that might affect the risk. But the examples that we have seen were of 2 risks. So I don't know if this model could keep being, we could trust this model with, let's say, 20 risks in 2 years. That is what has happened in the last, since 2020. Does this hold for many, many risks, or the model starts being less, I don't know how to say, less precise if we add more risks?
Yeah, this is a starting point, and 2 is really a lot more than 1. And if I started by writing down the kind of scenarios that the central banks are designing, you would have no idea what kind of probability to put on them. And so I think the central banks are going to have to at least come up with some mental picture of how plausible these scenarios are. And they rely on science for the answers. And science really doesn't give you the answers. Science only says, well, here are 4 possibilities. Take your pick. And who is picking? I mean, anyway, I think this is a conversation we'll probably have tomorrow. But in any case, in reality, this is very hard to do. But this is what you want to be able to do.
So, Eva?
Maybe we could also look at the other tail of the distribution, of the right tail of the distribution, if we were looking maybe at inflation risks, or the price of electricity, where the risk may come from the gas, the drought, or any other thing, and it would be just the similar approach.
Yes, I thought that would be an interesting example to do too. I thought about doing it with. I mean, you can do inflation and unemployment, even though they're sort of opposites, but we don't think they're actually so opposite necessarily anymore, because we're so worried that by trying to fix inflation, we're going to create a recession. So we could look at historically how often did those both happen, and the answer is fairly often. Whenever we had high inflation, we ended up with recessions that followed it. So, we can do that kind of stress, and the central bank has, I believe, no idea how to do both an unemployment and a market decline and an inflation exercise together and combine the results.
And also linked to sustainability and to climate risk included in this,
Yeah.
this setup.
Thank you.
Any questions, even if it's not finance? I mean, you don't get a Nobel every day until anyone from this department get it, and it will take a while. But, no. So any idea? You were mentioning, Rob, difficult to have a model, but in one of these items for the future research, you talk about predicting. So some type of model you may have in your mind or no? I mean, if you want to predict this.
For the betas?
Yeah. Or for the, yeah. Betas, lambdas, everything. I mean.
Well, I think of the lambda as being a function of the unconditional distribution, in which case, I guess I was thinking I wasn't going to try to predict it.
Okay. So only the
but
betas?
That may be the problem. I mean, it's an amalgam of times when maybe lambda was big and when it was small.
Yep.
So what is it we want to stress? Well, if you think the stress is something that you want to continue to do the stress, and then sometimes it becomes more severe than others, I think you want the unconditional distribution.
Okay. But that can be predicted.
This is not the banks are not forecasting. When they do the stress test, it's not a forecast. It's somebody's idea of what's something that could go wrong that you didn't think of.
So it's about the scenarios. So they have
it's
different.
The scenario, right?
Yeah.
So my alphas and lambdas are all about the scenarios.
Okay.
And so they're subject to needing to be looking in the future, needing analysis, needing models, and needing evidence from the past.
Okay. So, yeah. Pilar.
Here. Very small, just commenting on what you say. Could we think about your method as putting probabilities to scenarios, forecasting?
Yes.
Realistic probabilities to a scenario.
That's what I'm trying to do. And I'm picking a simple case where I can sort of do it. And I think what bankers will tell me over and over again is, I don't want to put probabilities on the scenario, but then how do you combine these scenarios? How do you combine the losses one way or another? Somehow, and how tight is, you have an extreme and a moderate scenario. Well, what's the probability difference between these two? I mean, somebody's got it in their head what it is, and they say, oh, we don't have to worry about this one because this isn't too extreme, but we'll worry about this one. Well, yeah.
Any further questions? I have to say that when you were presenting, I was seeing your way of doing research, so I forgot there's one more item that I tried to learn from him. Is very deep things, trying to make it simple. But you see, sometimes it's not so simple. So still, well, it's a problematic thing, but I was seeing your way of working while you were passing slides and slides and slides. They look simple, but they are very, very, very deep. So if there are no more... Isabel, yeah, sorry.
Do you have any thoughts? I think it's becoming more and more difficult to forecast the crude oil price. Could you give us some hints on how could we use this to maybe help to improve forecasting oil prices?
So you want to forecast, or you want to know something about the tails?
Well, yeah, okay, probably both, but how probably it makes more sense to know to use it to know more about the tails. Yeah, how would you?
Yeah, so I mean, I think we learned something by looking at the frequency of tail events in the past. I mean, crude oil prices, real crude oil prices, I suppose is what we should use, have fluctuated a whole lot over the last few decades, and so I think anybody that's, trading crude oil has in their minds what we've seen before. And they're probably forecasting whether things are more unstable or less unstable in the future. And so maybe they expand the tails a little bit because who knows when this war is going to be over and what the implication is going to be for the world energy market and so forth. So I think looking at what the tails look like in the past is informative. And if you look at the individual events, you might say, this event is never going to happen again. So maybe we throw that out of the data set and we look at the tails of what's left over, something like that. But maybe there's another event which is equally likely in the future, but is a different anyway. So I think there's a combination of empirical and theoretical analysis that I would recommend for doing that. And maybe building a full forecasting model of oil is a good way to do it. If you build a forecasting model for oil, and then you look at the distribution of the errors, and they look like they're all sort of IID and everything, then you can look at what the extremes were of this model, and you could probably simulate it over a million-year period and just see what the tails were.
Okay, thank you very much.
So I can remind all of you, Rob became famous for going beyond the mean, so he went to the variance, then later on he got, well, the variance is also a correlation, so he modeled dynamic correlation, and now he goes beyond the variance dynamic correlation, and now tail events. I don't want to ask what is next, so I will wait for next time you come. I have to thank a person that I forgot, and it's the last person who asked a question, Isabel Figueroa, because she allows us to kidnap Rob for a few hours. Thank you to all of you for coming, because I know it's no bad time, but it's at the end of the academic year, it's always a bad time, so exams, And well, you have to study, you have to prepare the exams, so pass all of them, please. And thank you, Rob. Great, and thank you for coming.